In this lecture, we're going to look at Newton's third law. This is the final of Newton's laws that we're going to look at. Now, this law actually relates the interaction of two different objects with each other. So we've only looked at forces acting on a single object. Now this is looking at pairs of objects. Now this interaction, it can happen when two objects touch, like having a cup on a table, or it can happen at a distance, like the gravitational attraction between the Earth and the Moon. And Newton said when two objects interact, there's always a pair of forces involved, and these are often called action-reaction forces or action-reaction pairs. And he had some rules that governed these forces. He said, when two objects interact, there's always two forces. These forces are always the same size or the same magnitude. They always act in opposite directions, and they're always the same type of force. So if one of them is a pull, the other one is a pull in the opposite direction of the same size. If one of them is a gravitational attraction, the other is a gravitational attraction of the same size in the opposite direction. We're going to look at this example of a dog pulling on a lead to demonstrate a couple of examples of action-reaction forces. So we know from this picture that the dog is exerting a force on the lead. He is pulling that lead with his teeth. According to Newton's third law, if the dog is exerting a force on the lead, then we need an action-reaction pair where the lead also exerts a force on the dog. And remember, it is equal and opposite in direction. And we have an equilibrium situation there because there's two objects interacting and they're not moving anywhere. Now there's another type of action-reaction pair in this diagram. If we say that the dog is exerting a force on the earth or on the ground, then there must be an equal and opposite reaction force. The ground must be exerting an equal and opposite force on the dog. So in this situation, these are our action-reaction pairs. We have the dog pulling on the lead pulling on the dog pushing on the ground, and the earth pushing on the dog. And they fulfill those requirements. They're all the same size, they're in opposite directions, and they are the same type of force. We can also apply this law to collisions. So we're going to look at a collision between two objects here. So here we have a ball hitting the head of a football player, or the football player's head hitting the ball. It doesn't matter which way you look at it. And we have a nice action-reaction pair to look at. We have the force of the player's head on the ball, and we also have the equal and opposite reaction force of the force of the ball on the player. And that's a force, if you ever headed a ball, you can actually feel yourself. So you know that these forces exist. But we also know from experience that the ball is going to move away from the player. And we also know that you recoil a little bit from the ball. One easy way to get confused in this is to consider the fact that these pairs are equal and opposite, so they must balance, so therefore nothing's going to move. But you've got to bear in mind, when we look at balanced and unbalanced forces, that's looking at a single object. So if we were just to look at the forces exerted on the ball, then we'd have to get rid of this one. So this is when we're looking at balanced and unbalanced forces. We can see now, if we just look at the ball is going to move away. And similarly, if we were to look at just the forces on the player, you could see that there's one force exerted on the player and he's going to move away. Obviously he's not going to accelerate away as fast. As we mentioned, F equals ma, force equals mass times acceleration. He's got a much bigger mass than the ball, so with the same force he's not going to move as fast. But that force exerted on the ball, which has a much lower mass, is obviously going to move away much faster. It's going to accelerate at a greater rate. So if you look at the objects together, you've got an equal and opposite pair of action-reaction forces. If you look at them individually, you can see the balanced or unbalanced forces that are acting on an object, and you can figure out what's going to happen.